So I want to go over a few things. We've touched on these before, but I really want to keep them at the forefront of our awareness of what inferential statistics really is. And the majority of what we've done is inferential statistics. That would be anytime there's a population that we're interested in, which might be everyone in the US, or it might be all kids between the ages of 13 and 18, or it may be people who have suffered from anxiety disorders, or it may be elderly patients who are admitted in long care facilities. Whatever that population of interest is, in many cases, we simply can't collect data on every person in that population. And so we take a sample. We take a small group of the population, conduct a little test or survey or study on this small sample, and then whatever results we get, we use statistics to estimate what we would expect to be true about the population. And that's where the confidence interval comes in, because we can't be exactly sure that the sample is like the population, but we use the sample to make rough estimates, give or take a little bit, about the population. So that whole process is called inferential statistics. The other part of statistics would be descriptive statistics, and that's where you're just taking a group and you take their average, or you take their standard deviation, or something, but you have data on everyone in the population in that case. So most of what we've done has been inferential statistics. And this whole process works wonderfully in general. It's a very cost-efficient, time-efficient, energy-efficient way of finding out about the population in a reasonable way. But it has some caveats, and that's especially where I want to focus here. In particular, this whole process depends on this idea that the sample represents the population. What does that mean? So one way we could say it is the different qualities about the sample should be seen in the population also. For example, whatever the average age is of the sample, we should see roughly the same average age in the population. What percent are female, black, white, Hispanic, those should be roughly the same as in the population. Although, I do want to add that oversampling is this idea where you have a small minority group in some way, not just racial minority, and so you sample them at higher rates to get more information so that you can make comparisons. That's perfectly valid. Excuse me. It's actually a wonderful thing to do. What you do need to be aware of is if a sample did that, if a data set did that oversampling process, you really should find a variable that's labeled something like weights, and you can put that into, when you run your statistical test, there's a little place to put the weights. It's pretty complicated how it adjusts for those weights, but it basically makes it back so that the sample now represents the population again. If you don't do that, typically the results aren't going to be off by that much. So sometimes I'll just run analyses without that weighting. Sorry. And then if I'm going to do it for a published article or something more specific, then I make sure to include those weights. Bottom line is the sample should look like the population in terms of averages, is what, when I say look like, averages and percents of the different groups should be roughly the same. Now, there's one really beautiful way to not guarantee perfectly, but get pretty close to that, and that's called random sampling. So if we somehow have a way of listing out the population, and we can use a computer program, whatever, to randomly choose a certain number of them and include those in our study, that is almost guaranteed that we can make a nice prediction about the population. There's still something called sampling error, so we still need a confidence interval there. But the point is, whatever we find out about the sample there, we can know, give or take a little bit, a pretty good idea about the population. And that's often what we have in surveys or observational studies. The advantage of doing them is that it is a little easier to take a random sample, and then we know that the sample is representative of the population, reasonably representative. Unfortunately, things like experiments, which are really good for making a causal claim, which are really good for saying that this treatment was more effective in the lab setting than this control for this group of people. Experiments are great because of random assignment. Random assignment is different than random sampling. Random assignment, which is part of experiments, is saying we already have the sample collected. So the randomness there isn't about choosing the sample. It's about once you have the sample, you try to figure out which ones are going to get the treatment or one of the levels of the treatment and which group is going to get the control. And because this is a random determination, you're balancing out those groups on all of these factors like age, race, anxiety, all these kind of lurking variables. So that when you get a result, you can say the random assignment process lets you say, well, that was probably because of the treatment itself, because the groups are balanced in almost every other way, other than the fact that this group got treatment and this group did not get the treatment. So that helps you tell that a result is true. But when we then go to say, since that result was true for this group in our study, we can then be pretty sure that that result is true for the population. That we run into some problems potentially, because in an experiment, because it is more intrusive, it is more a true experiment, you're somehow getting manipulated, and you have to consent to that, and you can't really just randomly pick people for an experiment like you can for a survey or an observation. And so you need these, you've probably seen them in the grocery store where you have like this experiment, and then there's like phone numbers dangling on the side. You rip one off and call if you're interested, if you want to volunteer for the survey. So it's a voluntary sample, a convenience sample, in order to do the experiment. So once the experiment is done, if there's random assignment, we can say that whatever effect that was observed is true for that group, and using statistical methods, using inferential statistics, people or animals or whatever you're studying that are similar to that convenience sample you had. Now, to make the argument that that convenience sample is representative of the overall population you're interested in, that's where you could potentially run into some big issues. So even though we do know that the random assignment tells us that whatever it was is true for the sample and those people in the population who are similar to the sample, it may very well not be true in general. Let me give you an example. Let's say that you just happen to get mostly poor men volunteering for your study. I mean, maybe they need some money more, and maybe the area just happens to be more heavily male influenced or something. So you get mostly male. So that result you have may very well be true in general for poor males, but then to say that that is true for people of any socioeconomic status, male and female, that's where you could run into some problems, depending on what it is. If it's something that's true about all of us biologically, and it doesn't differ by race or socioeconomic status, then it's probably legitimate that sample is representative of the population. But if there's any way that you can say that the sample doesn't represent the population, to the degree to which they could be different, there's more and more lack of potential validity in the results. Doesn't mean they're useless, but the greater the difference there, the more you should be cautious in interpreting them. So ideally, I mean, the ideal would be you take a random sample of the population, and so that's gonna let you generalize back to the population, whatever results you get, and then within that sample, you randomly assign people to treatment or control. But the truth is that that just simply isn't practical in most situations. It's possible to get the random sample, but then you have all the issues with lurking variables. Or it's possible to get the random assignment inside once you have the sample, so you can control for the lurking variables, but then you have more issues generalizing it back to the population. So it's hard to get, but there are some things called quasi-experimental methods, propensity scores, instrumental variables, regression discontinuity. These are fairly new techniques that are trying to get the advantage of both of those types of randomness at the same time, but they're still not perfect. There's issues with those also. One final thing I want to mention in all of this, in inferential statistics in general, when you are reading a research article, you're reading about what you see in the sample. So maybe you read that in the sample, the black participants in your sample were less likely to experience anxiety than the white participants in your sample. So that is very true for, assuming everything was measured well, is very true for your sample. But is it possible that the result was not statistically significant? Absolutely. What does that mean? That means statistical significance means whatever result we saw in the sample was so strong that we believe it's also true in the entire population. That's a pretty big jump. That jump of making an inference is a big jump. And so that's why you can't just look at what you see happening in your sample and automatically say, oh, we found something statistically significant. The whole point of statistical significance is saying that the result we saw in the sample was so strong that when we look at the confidence interval, whether we take worst case scenario or best case scenario, we're pretty sure that that same result would be true in the population. We might not know exactly what that result size is. There's usually a confidence interval on the effect size. But statistically significant is saying the results are so strong that it's true in the population as well, probably. So what could happen is you could have in the sample a result that seems strong in the sample, but when you run it through the statistics, you find that it's not statistically significant. That would just say that, yeah, the result really did exist for these people that were included in the sample, but it wasn't strong enough to convince us that we would see that same result in the entire population. So that's inferential statistics in a nutshell, with some of the things to be aware of two randomness tools that come into play and the strengths of each one.